Hi everyone, my name is Wentao, and I am excited to present SORNet, Spatial Object-Centric Representations for Sequential Manipulation. This is a joint work with Chris, Karthik, and Dieter. So in sequential manipulation tasks, a robot needs to constantly reason about spatial relations among different entities in the scene and plan its actions accordingly in order to achieve a desired goal. In the example shown here, this is achieved by a task and motion planner operating on top of a state estimator, which outputs exact 60 poses of the objects using 3D object models. We call this combination of a state estimator and task and motion planner the model-based approach. They're widely adopted in robot manipulation literature due to their effectiveness on real robots. These methods use handcrafted state representation that enables explicit reasoning about objects, as well as the object states, such as 3D location and orientation. However, estimating the handcrafted states often requires 3D object models or accurate object detection and segmentation, which limits the applicability of such methods to a set of non-objects. An alternative to the model-based approach is the end-to-end approach, which has also achieved a stream of success in robot manipulation. End-to-end methods avoids estimating explicit object states by learning an implicit representation from raw sensor observations that is optimized for the end task. However, because there's no explicit notion of objects or object states, these methods lack the ability to do structured reasoning. Consequently, it is difficult to deploy the learned policies on a task or goal not seen during training without acquiring additional training data or demonstrations. We would like to introduce structured reasoning into the learning process, and we believe the notion of objects plays an important role. Therefore, we propose a framework that learns a set of embedding vectors parameterized by object entities instead of a single representation for the entire scene. Our approach is explicit about objects, but implicit about object states. In this work, we present initial evidences that this framework allows generalization to both novel objects and novel tasks with little or no annotated data. Our idea of object embedding is inspired by recent works in visual question answering, but different from these prior works, we remove the dependence on object detection and segmentation entirely and show applications on complex manipulation scenarios. We propose a general framework for learning object-centric embeddings named SORNet, short for Spatial Object-Centric Representation Network. The input to SORNet is an RGB image plus a set of object queries. Each object query is represented as a thumbnail image, which we call canonical object view. The RGB image and canonical object views are passed through the embedding network, which produces an embedding vector for each of the query object. Then, a set of readout networks takes the object embedding and outputs logical states with the query objects as arguments. Note that the canonical views can be captured in settings different from the current scene. For example, we can use canonical views from simulation on real-world images. Further, for any object, only one canonical view is used to do any prediction related to the object in any scene. Thus, the canonical object views place little limitation on the applicability of our method. Let us now take a look at the architecture of the embedding network. The input to the embedding network is an RGB frame plus the canonical object views. The input frame is first split into patches, which forms a sequence of image patches together with the canonical object views. The sequence of patches are flattened and linearly projected into a sequence of vectors. We add positional encoding to the sequence and then encode it with a transformer consisting of multiple multi-head self-attention layers. We take the embedding from the final self-attention layer corresponding to the canonical object views as the output object embeddings. Our embedding network is based on the vision transformer backbone, which provides several nice properties. For example, we can change the number of object queries or switch the order of the canonical object views, and the output object embedding will change accordingly without any modification to network parameters. To train the object embeddings, we leverage logical predicates from task and motion planners. These logical predicates encode spatial relations among objects and the environment. For example, whether the robot is holding an object or whether one object is stacked on top of another. Our network is not trained with any object masks, bounding boxes, or 6D poses, but optimized directly to predict these logical relations. This allows the learned object embedding to focus on information relevant to spatial reasoning, rather than being distracted by other factors, such as camera viewpoint or object symmetry. The logical predicates can be obtained from the object embeddings using the Readout Networks, which are essentially a collection of two-layer perceptrons, each responsible for a type of spatial relation. Here, we show the operation of a unary readout network, which output predicates with a single object argument. Here, the network maps the embedding of the blue block to the predicate with the blue block as argument, and does the same for all other object embeddings as well. There are also binary readout networks, which can predict predicates involving a pair of objects as argument. The network takes the concatenation of two object embeddings and predicts the predicate value with corresponding objects as arguments. Note that the number of outputs by the readout networks changes adaptively with the number of input object embeddings, which enables the overall network to generalize to an arbitrary number of query objects without modification to the network parameters. Now let's look at the experiment results. We first evaluate SORNet on a task that it is trained on, classifying logical predicates from RGB frames. We build a simulation dataset where a robot arm performs sequential manipulation tasks with a domain randomization. The training sequences always have 4 objects with the same goal condition, while the testing sequences have objects not seen during training, different number of objects, and various goal conditions. SORNet achieves almost 99% accuracy, significantly outperforms baselines that have no object conditioning. Moreover, distractor objects, different number of query objects, and transfer to real-world images cause only a slight drop in performance. Next, we demonstrate how SORNet's prediction can be useful in real-world planning. Here is our experiment setup. On the tabletop, there are 4 colored blocks that were not seen during training and a Franken robot arm. The table is divided into 4 overlapping regions. Given an input RGB frame and a set of canonical object views as queries, SORNet generates a list of logical predicates indicating the current state of the objects. Given a goal specified as a list of conditions to be satisfied, a task and motion planner takes the predicted predicates and generates a sequence of actions towards the goal. Note that our network is trained entirely in simulation without seeing any of the test objects here. Although SORNet is trained on predicting logical predicates, we found that the learned embeddings are also able to capture continuous spatial relationships. In this experiment, we show that readout networks can be trained on frozen SORNet embeddings to regress continuous quantities, such as relative directions between entities in the scene. The fact that continuous quantities can be predicted from SORNet's embeddings opens up many potential applications. For example, in the video here, we use the predicted 3D direction from the robot's end effector to the object centers to guide the robot to reach a target object using position control. Quantitatively, readout MLPs trained on SORNet's pre-trained embedding also outperform networks trained from scratch as well as networks initialized with other pre-training methods such as CLIP. Finally, we also evaluate SORNet on predicting spatial relations on the Clever Cogent dataset. The dataset contains objects of different shapes, sizes, and scenes with up to 10 objects, which lead to very heavy occlusions. The training and testing split also contain different sets of objects. SORNet exhibits almost zero generalization gap to unseen objects and achieves similar performance to an Oracle baseline trained on both training and testing objects. If you're interested, please refer to our paper or come to our poster session for more details. Thanks. I'm happy to take any questions from the audience.
Are there any questions? We got a chat. Yeah, there's one there. Which one, sorry?
Really nice results. I have a question about the readout network. So it seems like the predicates have to be hand specified. And so I wonder if you have thoughts about, firstly, how that scales, and secondly, if you can add specific predicates in an ad hoc fashion.
Yes. So during training, then the predicates, the types of predicates is hand specified. But just as we shown in the continuous regression experiment, we actually treat the XYZ components of the 3D direction as just another type of predicates. And you can easily train new types of predicates in a few shot fashion.
Mm-hmm. Okay. Yeah, one more question here.
Sorry, were you?
Yeah.
No. Yeah. I also have some question about the predicates. It looks like in order to retrain this predicate, you need label data. For example, you say the blue is on, the red is sexual. That given the different combination, doesn't mean that you have to manually do a lot of these labels.
Yes, that's true. But these labels, first of all, it's pretty cheap in simulation. And second of all, we only need it for the non-objects, and you can just generalize the same type of relations to unknown objects. So we believe, even though it's still heavily supervised right now, there are still potential values. And of course, in the future, we're gonna explore directions with more sparse supervision. Thanks, very good question.
So, yeah.
Mm-hmm.
So, hi.
Yep.
Can I ask you something? What happens if all your cubes are the same color?
So currently, the framework doesn't handle that. Actually, in the Clever data, there are things with repeated object, and if there's no ambiguity in the relation, then network can actually accurately predict them. So in order to deal with multiple different instances with exactly the same appearance, I think you can, for example, pass some other conditioning input in addition to the canonical object views. And the transformer network will be happy to take that. And it
Doesn't it make sense to try to use the like NLP style already in your network and not have a two-stage process there? So, because I think the part of predicting the predicates is already presented in some sense in previous works. So wouldn't it be this kind of a way to resolve this kind of ambiguity, that you have kind of a semantic embedding and not only basically this coding that you had with this single view, canonical view, as you called it? Because I think it's just encoding the RGB and green that your cubes had. Yeah,
it's definitely implicitly doing sort of object detection. But yeah, I think what you said makes sense. But I do think that two-stage, you mean like, I think there's value in first obtaining generic object embedding and then use these readout networks to sort of read out any properties you want from these object embeddings. So it can reserve most of the parameters in the transformer backbone and just like generalize to new types of predicates in a few short fashion. So I think that's good to keep, but the conditioning on the canonical, like the image patch themselves, can be modified. For example, we have some future plans to use like multiple canonical views for the same object that could help. And also other types of conditioning also might help.
Thank you.
Okay, one more question.
Yes, so it's partially connected to what George asked. So actually it's two questions. So one is how large is the data set for training all these networks? And second is whether you compare to, let's say, classical bag of words based approaches with dictionaries that you can learn incrementally that would enable to learn like any objects or entities for multiple views without having to decide a priori how many and like assign the labels and so on, which are also lighter, I would expect, in terms of computation.
So this data set, so first question, the data set contains about, I think, 1 million images. So that comes from like 10,000 simulation sequences. So it's a pretty large scale data set that allows this general object embeddings to be trained. And the second question, I'm not familiar with that, what you're talking about, like the semantic.
It's bag of words. So in computer vision, before nets learned from anything, but they were extracting features, you know, and then you create this bag of words and you create a dictionary. And then because entities, so when the robot explores, it can create a dictionary for every object, every entity, and then you can say this is object 1, object 2, object 3, and then you accumulate views over the object. You can also take it in the end or do manipulation with that. And actually, they also work well in stacking and combining objects and stuff. It was like, if you look papers in 2012, let's say for some years ago, in computer vision, it was like.
Yeah, I think, so we choose to specify like what we are interested in advance. We just don't know where they are. We know what we're interested in advance because it just works well in practice. Actually, there are a couple of even more recent works related to what you're talking about. I remember one called like attend, infer, and repeat, something like that. That can just taking a single image, like infer both how many objects are there and what their entities, what are their appearance, and so on. But it's this type of approach, just there are too many entangled factors, and it's really hard to make it work. And no one has shown, it's only been shown on very primitive shapes, very simple things. And no one has really applied it to, say, real world manipulation images with the robot arm. But if that can work, it's nice, yeah.
Have a look because it's very easy, because once the camera is calibrated, when you get these features, you automatically have 6D representations. So for grasping objects identified in this way, it's very easy.
You say camera is calibrated. What if the camera view is changed? Then you won't generalize?
You recalibrate.
Yeah, we can take this question offline. Very, very good, interesting discussion.
Yeah.
Great. We've got one question online. So Danfei Xu from NVIDIA says, the main advantage of the method is that it works without post estimators, but don't you still need post estimation for motion or skill planning? For example, in the block stacking example?
Yes, that's a very good point. So the current framework is only high level, so it assists the task planning aspect, but not entirely fully support motion planning yet. So it is correct that in these real world demonstrations, you still need post estimation for the actual motion commands in the primitive skills. And this is an important future direction we want to explore, is having more fine-grained spatial information to support these low-level or more fine-grained control to basically get rid of post-estimation in both high-level and low-level. Yeah, that's a very good point.
Great. I think that's all on the remote side of things.
Seems also the case in the room here. I don't see any more arms. Yeah, so thank you, Wentao, again, and also for the lively discussion. And yeah, this concludes the session.